Take it away.
All right. Thank you for tuning in again. So today we'll continue our discussion of where we left off in the last lecture. So let's briefly go over what we discussed at the in the last lecture. So last time we tried to interpret homological algebra as representation theory of certain Hopf algebras and try to generalize from there. So the slogan was homological algebra is representation theory of a very particular graded Hopf superalgebra, which is KD over D squared, or AKA the cohomology ring of the U1 compact Lie group. So, and we asked ourselves the questions, are there other features of homological algebra for H modules, for general Hopf algebra and cohomology for H modules, or triangulated structure on the H modules? So we went back and re-examined the cohomology of chain complexes using this language and found out that taking cohomology is a way of killing projective injective objects. And to generalize this to arbitrary H modules, so we use the classical theorem of Larsen and Splitter, saying that Hopf algebra has projective modules equivalent to its injective modules if and only if H is a finite dimensional Hopf algebra, so it's Frobenius. And taking this categorical quotient of its representation category H mod by projective injective objects is equivalent to constructing the stable category of H modules. And last time we have given a construction of how to measure the morphism spaces in the stable category in terms of its so-called element integral, which is a copy of the trivial representation inside the left regular representation of H acting on itself. So the theorem is that how big the morphism space is in the stable category is given by the subquotient of H invariance in the inner Hom space. That's equivalent to the H intertwining homomorphisms modulo those coming from applying the averaging operator lambda or integral operator lambda. So this is how we prove it. And last time we stopped here when we thought about when H is the group algebra of a group, then H is Frobenius if and only if G is finite. And this happens by using the formula we have derived last time, that this is equivalent to the Maschick's theorem. Kg is semi-simple if and only if the order of G is invertible in the ground field. So, and likewise, let's analyze this for the usual homological algebra case. So H is the graded Hopf superalgebra KD over D squared. And if you're given two graded modules over this very small Hopf algebra, you can reinterpret them as chain complexes over K, right? So this is what we have been emphasizing. So, so given two chain complexes, how do we measure their morphism spaces in the stable category? So, so by definition, this is the numerator is going to be all those maps that are H invariants, but this Hopf algebra is generated over D. And using the H action on the inner Hom space, you can easily work out that the action on any K-linear map is just given by taking supercommutator with D. So in particular, a K-linear map is H invariant if and only if it supercommutes with the differential operator D. And in the denominator, these are all those chain maps that can be obtained by applying D to K-linear map H. So these are all those maps that has the form that's a supercommutator of D with this K-linear map H, also called a null homotopic. So in particular, this Hom space agrees with the usual Hom space in the homotopic category of chain complexes over K. So in particular, this stable category just recovers the usual chain complexes of complexes up to homotopy. So, and for the third example, we have been focusing on, so this is K, H equals K partial over partial to the pth power over a field of characteristic P. And whenever you are given a two graded module, and measure how big the morphism space is in the stable category. So the same analysis applies as in 2. So here, again, D acts, because this half algebra is generated by a single operator D, and all those maps that are H invariants are precisely those maps that commute with the differential operator. And all those maps that are in denominator are those obtained by applying the integral operator D equals P minus 1. So this integral operator applied to some linear map H. So D to the P minus 1 dot H. And the small miracle in characteristic P is that when you work it out, all these binomial coefficients minus 1 to the ith power of P minus 1 choose I becomes 1 in this case. And so you obtain this sum of D to the I composed with H composed with D to the P minus 1 minus I. So in particular, when P equals 2, this agrees with the case 2. So the half superalgebra and half algebra in case 2 and 3 agree actually in characteristic 2. So that's not surprising. Okay, any questions? All right, so for this comparison of 2 and 3, we'll make the following definitions. So again, for over a field of finite characteristic P, H equals KD over D to the pth power, then any graded module would be called a P complex. So it's like a complex, but the differential operator satisfies that D to the pth power equals 0 instead of D squared being 0 as in the usual complex case. And the stable category, as we have seen, is an analog of the usual homotopic category we mod non-homotopic maps. So these are so this is called the homotopic category of P complexes. Okay, so and the reason so why do we want to consider the homotopic category of P complexes? So why do we care about them in connection with categorification and roots of unity? Is because of the following really beautiful and simple observation of Kavanagh and Bernstein. So they observed that whenever you have a half algebra and in particular finite dimensional half algebra, you can construct this stable category. It inherits this tensor triangulated structure. It inherits this tensor structure, and this tensor structure is actually compatible with the triangulated structure on the stable category. And furthermore, the Grothendieck ring of this stable category for KD over D to the pth power, this very particular half algebra we have been considering this guy, the Grothendieck ring is actually isomorphic to the cyclotomic ring at the pth root of unity. So, and this is the base ring where the quantum invariants, 3-manifold invariants should be living over. So that's why this is this H graded underlying mod is a categorical analog of this ring. So again, just as in the one of the previous slides, we have seen that the usual homological algebra is a lift of Z or ZQQ inverse. You also have all these abelian operations like taking direct sum, taking tensor product, homological shift, and gradient shift, and they decategorify, or when you pass to the Euler characteristic level, it becomes addition, multiplication by -1, and this root of unity Q in this ring. All right, so let me briefly sketch how this is proven. So the tensor product descends to the stable category is relatively easy. So it essentially boils down to checking that whenever you have a projective injective object, and when you take tensor product with an arbitrary H module, it still remains a projective injective. So this projective injective object becomes an ideal in the under tensor product. Okay, so but the proof of this fact is relatively easy. So it's essentially the same as what we have observed in the proof of Mashiki's theorem. That you use tensor Hammond junction in the H module category. You can see that if you have I injective and tensor product with arbitrary M, Hom of this into something is adjoint to Hom of I into M star tensor, Hom of M into something. So using composition of exact functors, you can see that this guy is also exact. So it's injective. And secondly, whenever you take the tensor product of a short exact sequence M with which defines the homological shift, it remains exact because this tensor product is over the ground field. And so you show that this shows you that tensor product with an arbitrary module actually commutes with the homological shift. And likewise, it commutes with forming the cone. So it's a tensor product with this push-out diagram remains a distinguished triangle. Oh, sorry. Oh, I guess that slide was repeated. So therefore, the Grothendieck group of this triangulated category, well, by definition, the Grothendieck group is generated by the Z-span or Z-span of objects in this category, modular relations. So whenever you have a distinguished triangle, so whenever you have M, N, L to homological shift, you get a relation that N equals M plus L. So I should probably have written this down by definition. Then, so this is the Grothendieck group of a triangulated category, but it inherits this tensor product structure on H gradient mod. So it inherits this multiplication structure. So it's a ring, and the trivial module K underlying becomes the multiplication identity, and K shifted by I is the gradient shift on this category. Okay, and descends to multiplication by Q. So for this particular H graded mod, for this particular H equals KD over D to the Pth power, you can see that the triangulated category is generated by the simple module, because this again, as for chain complexes, the objects are really easy to classify in this category. They're classified by Jordan blocks of size P or smaller. So, and so they give you all the indecomposable objects in this category, and all such indecomposable objects can be filtered by gradient shifts of the trivial module. So it's easy to see that the triangulated category is generated by this guy. And the only relation we have killed in this construction is that the free module up to gradient shift becomes annihilated in the quotient category. So, but the trivial, this module, the free module up to gradient shift, is just a multiple q to the ith multiple of the cyclotomic polynomial 1 plus q instead of q squared here, plus all the way up to q to the pth plus minus first power. This is the minimal polynomial of e to 2 pi over p, if you think about it. So that's why you get this isomorphism. Nice observation of Bernstein-Kovanov that this Grothendieck ring is precisely the cyclotomic ring at the pth root of unity. Okay, so now, so just as how we utilize homological algebra, we want to utilize this categorical incarnation of the pth cyclotomic ring. So we interpret H underlying graded mod as categorical version of OP. So there are many further questions we should be asking ourselves at this point. So first off, how can we categorify modules over OP? And so this will be like linear algebra over OP. And secondly, how do we study ring theory over OP, or categorical ring theory? So how do we categorify algebras over OP? And the particular ring we're interested in is the quantum group UQG over OP, where q to the pth power is a root of q to the pth power is 1. So, and even further, how do we categorify modules over UQG and their tensor products? So we'll be gradually shifting towards these questions in this lecture series. So we'll start with the very first question. Okay. So this brings us to the notion of how do we categorify modules over OP. So let's try to think about this. So in the usual homological algebra, when you want to find interesting Z modules from either geometric representation theory or from symplectic geometry or algebraic geometry, you try to produce some important categories, like category of sheaves or representations. like category O, or constructible sheaves in symplectic geometry. And these categories sometimes have very interesting Grothendieck groups. So that's the old sense of categorification. And these categories can usually be described when you take certain nice generators of these categories by their endomorphism algebra of their generators. But these endomorphism algebras of these generators are usually given by differential graded algebras, or their close relatives in infinity algebras. So, we take the simplest kind, so the differential graded algebras, by definition, is a graded algebra equipped with a super differential, dA, so that raises the degree of elements by 1, such that first off, d squared equals 0 because it's an algebra object in the usual homotopic category of vector spaces. And secondly, it satisfies the super Leibniz rule because it acts, dA acts by derivation on this algebra. So in other words, a differential graded algebra is nothing but an algebra object. It provides an algebra object in the homotopic category of chain complexes. Okay, and so to mimic this situation, so let's consider an analog of this in the P homotopic category. So a P differential graded algebra, ADA, is a graded algebra over a field of finite corrosive P equipped with a degree 1 endomorphism dA, such that it, first off, d to the pth power has to be identically 0, so it's it becomes a module over H, right? And secondly, it's a module algebra over H in the sense that the multiplication of A is compatible with the H action. So if you translate into that this differential language, this means that the differential dA acts as a derivation on this algebra. So d of AB equals dA times B plus A times dAB, which is the usual Leibniz rule. And similarly, you can generalize the notion of differential graded modules to this context. So a differential graded module, again, over a PDG algebra is again a graded module with a degree 1 endomorphism such that d to the pth power is 0, and its multiplication by A and elements of A and the differential are compatible in the super Leibniz, in the Leibniz sense. So this is dm of AM is the algebra differential dA times M plus A times dm of M. All right. So there are a lot of analogies between these two different worlds. So the usual differential graded algebra and the PDG algebra. So, but before that, let's think about some concrete examples that will also appear in the exercises. So first off, if you consider the usual polynomial ring over a field of corrosive P, and you define a P differential by setting dx equals x squared and extend it to the entire ring by the Leibniz rule. Okay, so then this becomes a P differential graded algebra. So this is an easy exercise to check, and you can try to determine how the differential acts on arbitrary basis elements of this polynomial ring as well. And secondly, you can consider the matrix algebra, and for instance, J is a direct sum of Jordan matrices of size less or equal to P, and define. But I should have emphasized that here J must have eigenvalue 0, so it's nilpotent, so it's like a Jordan matrix of this form, 0, 0, 1s. But when you restrict to the matrix algebra of size less or equal to P, then this becomes a P differential graded algebra. So d to the pth power is identically 0, and because it's a derivation given by taking commutators, it satisfies the usual Leibniz rule. And thirdly, when you take the first example and take n copies of its tensor product, so you get a differential graded algebra action, d action on the n variable polynomial ring. And because this action commutes with the symmetric group action permuting variables, if you set dxi equals xi squared for all i's, so it's invariant under permutation of the symmetric group elements. So it's preserved under this invariance of taking the symmetric group action on permuting the indices. So in particular, this symmetric group, the symmetric functions of in n variables sits as a p differential graded subalgebra inside the polynomial ring, n variable polynomial ring. So it inherits the p differential graded algebra structure, and there are actually some very nice action in terms of the differential on the basis of the symmetric functions. For instance, in the algebra basis by elementary and complete symmetric functions, you have nice formulas describing how the differential acts. And even furthermore, if you dig in further, there are actions on assured polynomials which have fairly interesting differential actions. So some of these have been left as exercises. So and it's worth trying. So now let's draw the analog between the usual differential graded algebras and the p differential graded algebras. So we can all start starting with the DGA or PDGA, you can all consider the abelian category of DG modules or PDG modules. So these are abelian categories. You can form tensor product, you can form direct sum and gradient shifts, etc., etc. So and kernel, co-kernel in these categories are well defined. Okay, so we have explained the notion of homotopy in this context. So you can model non-homotopy in these categories. So in the first in the usual DG world, so non-homotopy are those maps obtained by applying D to some A linear map between chain complexes. So you obtain a triangulated category. And here in the PDG world, you apply the D to the P minus first power to some A linear map to obtain the homotopic category. And we have also explained the notion of derived taking cohomology, which is you forget the A module structure on both sides and pass to the stable category of H. And so that's a forgetful functor. So inverting the kernels of the forgetful functor, inverting quasi-isomorphisms, you get the triangulated category of the so-called derived category. So on the left-hand side, you obtain the usual homological algebra, and the right-hand side, you get the new exotic PDG homological algebra. And all of the stories can be generalized to finite dimensional half algebra H. And so, so this is why Kovanov came up with this terminology called homological algebra, because it's a mixture of the usual homological algebra and the representation theory of H, so half algebras. So that's the generalization called homological algebra. So one key analog I want to bring your attention to is the following theorem. So why we were interested in this PDG derived category is that the PDG derived category dA of D of a PDG modules over A admit a categorical action by H underlying mod. And when you take Grothendieck groups of appropriate sense, so here to be really strict, here you can only take the notion of compact derived category. So that's like a finitely generated A modules in some sense, and analog of finitely generated A modules. So you don't have Eilenberg's window phenomenon in the Grothendieck group. And so you take the compact generated derived category and pass to its Grothendieck ring, Grothendieck group. You recover the action of OP acting on some module, K0 of A. So this is K0 of AD by definition is the K0 of this triangulated category, DC of A. That's something we really haven't discussed in this lecture, but it's a smaller subcategory of the big derived category so that the Grothendieck group makes sense. Okay. All right. So maybe it's a good point to take a small break, and it's close to the midpoint. So we'll pause for 5 minutes for questions, And then we'll continue with our second goal of categorifying algebras or interesting algebras that are interesting to us in this project in the talk.
Great. People can ask questions. We'll be back at 10:30, 1:30.
Hi, I have a very specific question.
Sure.
So I don't totally understand if this is like not the time to answer. So I was just thinking about, so typically when you're doing like if you have a Z mod P action on something, a spectral sequence that you would associate to it can take sort of, you look at the big upstairs object and then you look at its homology. Yeah, the quotient homology, and your spectral sequence has differentials like 1 plus x and then 1 minus x and then like the cyclotomic polynomial in
Right.
x. Is there an analog in the P complex that should also compute the same thing with using just the differential 1 minus x? Like, should I see in terms of like spectral sequences, if you have a story in the KD mod D squared story, is there an analog in the K partial mod partial to the P story?
That's a great question that I don't know the answer of, but I guess in general, when you if you think about the simplest case of spectral sequences coming from bicomplexes, that's from Kovanov's point of view, I think spectral sequences exist because objects can be classified over bicomplexes. But if you have bicomplexes over p-complexes, that's a wild problem. There's no, actually there is no classification of indecomposable objects. So we don't expect there to be a spectral sequence in that case. Right.
Yeah, there's lots of different homological functors you can define in that category, but
yeah. So yeah, in general, probably no, but maybe in some specific contexts that you limit the number of kind of indecomposable objects that appear, maybe there's some hope.
Okay, thank you. Is there some place that I can look at for any work that's been done with bicomplexes over P complexes? No, just a curiosity. So yeah, thank you.
No problem.
I'll mention that like almost everything that people do in homological algebra that sort of involves just cones or just two-term complexes and things like that have immediate PDG analogs. When it gets more complicated, it's not so easy.
Mm-hmm. Any other questions?
Can I ask a quick question?
Sure, yeah, go ahead.
So just notationally, what do you mean by quasi-isomorphism in this PDG world? Is it just kernel mod co-kernel of your element, or?
It's slightly more subtle. Yeah, there are analogs of homology functors on these categories, but a more uniform definition is so if you have a module over AD, you just forget the A module structure and regard it as a module over, so forget as a module over D. And if you have a morphism of PDG modules over here, F M over N, and you forget it as just MD and ND, and this induces an isomorphism in the homotopic category of P complexes. then you call that F is a quasi-isomorphism. So just as if this partial is the usual derivation dA, so F induces a quasi-isomorphism if it becomes an isomorphism on homology only. So when you disregard the A module structure.
Ah, I see. You're working over a field. So you're saying
Yes.
isomorphism in the homotopic category is your definition of quasi-isomorphism.
Yes.
Ah, okay. Got it. Thank you.
No problem. Yeah, great question.
All right, let's continue. Good question.
All right. So now let's move on towards a first candidate for categorification of algebras. So which interests us, which of great interest to us is UQ-SO2, or the quantum group SO2 at a pth root of unity. So why we want to do this is, as we have said in the first lecture, as a motivation that the quantum group appears in the rich thinking theory of Witten 3D TQFT as the quantized gauge group of so-called 3D transaminase theory. So when you try to construct 3D invariants of quantum 3 manifolds, you usually use the representation theory of quantum Hopf algebra to control the local data. So you assign to pieces of knots or links or pieces of triangulated 3 manifolds. And once they're compatible in some sense, you can glue them together using state sums and to get a manifold of the global object. So this, the quantum groups control the local data, and under compatibility conditions, they glue to give you a 3D TQFT. So in Crane and Franco stream, so this categorified 3D quantum groups would control local states you assign to 4-dimensional pieces of manifolds. So maybe these are quantized 2 gauge groups. I don't know. So they're still up to this day no axioms of Hopf categories. So no non-trivial examples yet. So it's a wide open question for everybody interested to explore. So now let's briefly review what quantum group quantum SO2 at a root of unity is. And I'll be using a diagrammatic notation to motivate what we'll be discussing. So because these are the quantum operators that control quantum states, so you know that SO2 usually is defined by its standard representation on a 2-dimensional space. Usually people write 1 or -1 as the eigenstates, and there are operators like E and F that acts on these quantum states. Okay, so if you draw this ones on some region and E like a spin chain or something, if you're familiar with this language, then you can draw this quantum operators on a line. So we're interested in this version of idempotent version of quantum groups. So where the regions are labeled by the weights of SO2, and so this E and F operators either raises weights by 2 or decreases the weight by 2. So we read these pictures from right to left. So lambda, when you encounter, so you think of lambda as some quantum state, and when you encounter F, it decreases to lambda -2, and E is increasing the quantum state from lambda to lambda +2. Okay, and there's just a 1-dimensional algebra structure on this operators. So you just multiply them by juxtaposition of or stacking pictures sideways. So when lambda and mu, so the rightmost region of the left picture of this picture, lambda agrees with mu. So you just put these pictures side by side and glue them together, or otherwise you declare the multiplication to be 0. So this is what idempotent algebra gives you. And so if you declare this to be an algebra, of course, this is not the quantum SO2 yet. Quantum SO2 or the usual SO2 would satisfy some relations discovered by Serre, for instance. So modulo the following relations. When you try to commute these operators E and F, you pick up some error terms coming from, so when you commute F past E, and or E past F, depending on lambda is greater or equal to 0, or lambda is less or equal to 0, you pick up quantum lambda copies of the identity transformation of the lambda region. Okay, so this is the usual SO2. But what's special about root of unity is the nilpotency. So this is E to the pth power or F to the pth power is always 0. So this is nilpotency relation. Okay. So any questions about the definition of quantum group in pictorial definition of quantum group? So this is just a one-dimensional structure where multiplication of elements are not commutative, but they're commutative in some controlled way. And when you commute them, you get some error terms like this. Okay. So because this, as you expect, these quantum groups appear in quantum field theories or topological quantum field theory. So when you try to categorify them, you want to introduce an extra dimension into the story. So to categorify quantum groups, we want to introduce the so-called time dimension to study the evolution of these quantum states. Okay, so instead of talking about these commutator relations, you should say how does one side of the equation, like EF equals FE plus quantum lambda times identity of lambda, evolve from the left-hand side into the right-hand side. So once you introduce an extra dimension, you have the freedom to talk about how does the right-hand side become the left-hand side in the when time changes, right? So when time shifts. So therefore, let me just give you an impressionistic point of view of what categorification is. So the rough idea is, so we'll have two-dimensional pictures like diagrams, and each horizontal slice will be an isomorphism class of modules EIFI. That will be the one-dimensional story of the quantum group. So the old quantum group is a horizontal slice you see in the pictures. And the two-dimensional pictures describe the evolution of these one-dimensional pictures, or these are really just maps. So evolutions don't have to be isomorphisms, right? So so they are just maps between those corresponding projective modules EIFI, or the of the corresponding one-dimensional slices. And sums of one-dimensional pictures becomes direct sums of modules of the two-dimensional pictures, and equality of one-dimensional pictures becomes isomorphisms of modules. So this is the rough idea, and let's see how this is done by Kovanov, Lauda, and Ruquier in greater generality. So, but for this talk, we'll just be presenting Lauda's diagrammatic calculus for UQS2, SO2, and this has a vast generalization to any quantum Kac-Moody algebra associated to any G. So, but this is the simplest and the most illustrative version to discuss. So we want to discuss how maps evolve among E's and F's. So here we have generators given by, oh, I forgot a dot, sorry. Generated by these guys. So you depict a morphism from E to E, or some interesting event happening between the evolution of E itself by a dot, or two copies of E by crossing. So this is a crossing. And these guys satisfy the following so-called Neo-Heck algebra relations. So whenever you see them locally in some picture, if you have many E's appearing, so here, maybe that's not a good picture, like this. So there is a double crossing in the between. So you use this a third relation, double crossing is 0, so to declare that this entire evolution picture becomes 0. Okay, so this is part of the Neo-Heck relations. Oops, sorry. And we have not only just E and F's, so E's, we have also F's in the story, so and empty regions. So to connect them, Lauda introduces cups and caps. So each horizontal slice, as we have mentioned, each horizontal slice is a picture of E and F. So this picture depicts an evolution from E composed with F to nothingness to the identity of lambda region. So this is likewise Fe, and so you have all orientations of the orientations of these states, these caps. So together with the neo-Hack algebra relation, neo-Hack algebra generators, they're bound to satisfy these relations, which I'll quickly flip through. So-called the bijointness relation. So these going up, things going up and things going down should be connected by cups and caps. And so-called bubble positivity. So you can use cups, caps, and dots to cook up bubbles, and they should be treated as independent generators. In fact, so it's better to regard them as independent generators and impose relations on them. So for this notation, I'll declare this clockwise bubble and counterclockwise bubble as follows. So there are some so-called fake bubbles that I don't want to maybe discuss for now, but if you're interested or know the story, you're probably familiar already. So, and all these curls can be reduced to bubbles plus dots. So this is reduction. And what's important, what's going to be useful for our talk is the so-called identity decomposition relation that tells you that how EF, this important relation, how EF can be two commuted in some way. So I'll explain what this means. Okay, so this is graphical calculus, which we denote by U. This calligraphic U is shown by Lauda to be non-degenerate, and where he showed that it acts on some interesting category coming from flag varieties across Grassmannians, and it categorify the idempotent quantum group at a generic Q value. Okay, so or in the homological algebra over this over this diagrammatic calculus is a two analog of the quantum group. So in some sense, Lauda's calculus is just a two-dimensional idempotent algebra where you not only have side-by-side multiplications, like in the one-dimensional slices, it has two compatible multiplications. Vertically, you can vertically multiply things and horizontally multiply things, and they're subject to topological moves. So far away interactions don't interact with each other. So this is truly topological in nature. So this idempotent calculus is also known as a two category in some in the jargon. So, but just think about this as a usual algebra, but has two compatible multiplications. So why Lauda's theorem is true? Let's try to illustrate why EF evolves into FE, as we have seen earlier. So as in our general philosophy, so EF now becomes a projective module. So these are all the things that have the algebra on top of it. So this is a top module, if you want to think about it, or left module, if you turn your head 90 degrees. So so EF becomes the horizontal slice, the bottom slice of all the pictures in below. So this is a projective module. And how does a projective module evolve into something on the right-hand side? So, so maps between E and F now becomes whatever picture you can fit into in between this projective module EF. So this is this module EF. And when you put some picture down below here that makes sense, for instance, sorry, FE, like this, then this entire picture now lies in FE, right? So this is how a picture in U describes the evolution of one projective module into the other. So this appending some picture to the bottom gives you an element of maps between projective modules. So in general, how do you show that there is a decomposition of projective modules? So usually when people say M is isomorphic to K direct sum L without much thinking, but essentially this means that you can produce maps, A module maps from M like projection maps UI to K and L, and inclusion maps V1, V2 back into M, such that they satisfy that the identity map of M is V1 U1 plus V2 U2, and the other way, when you go from K to go from K to M and back from M projecting onto K, you should get the identity of K, and likewise from L to M and M projecting back to L, you get the identity of L. And when you do the other way, mixed from L to M and project onto K, then you should get the zero maps. So this gives you the orthogonal decomposition of M into K direct sum L. And these elements U1, V1, this maps U1 composed with V1, V2 composed with U2 become orthogonal idempotents in this endomorphism ring. So this is why how you show two maps are two modules are isomorphic to a direct, one module is isomorphic to a direct sum of the two other modules. So let's go back to this this picture. So this projective module U times EF. So this is the projective module EF, and we can produce maps onto FE and many copies of the identity. So arbitrary closed pictures above the region of lambda. So this represents the object identity of lambda. So they're naturally, so cups give you these maps, and you put some dots on them. And to produce the inverse maps, you actually use the other sideways crossing and bubbles together with this. So this is a very natural way of constructing, and using the relation. Earlier, we have written down this identity decomposition, two analog of commuting E and F. You get that this diagram does satisfy that these maps give you a decomposition of orthogonal idempotents in the endomorphism ring of EF. So in this, as we have just explained. Okay, so consequently, these are orthogonal set of idempotents, and in the Grothlin group, you do have EF equals FE and plus not lambda copies of the identity lambda. Okay, so we call this context a factorization of idempotents. So it's very prominent in many in study of diagrammatic algebra. So the above story applies not only to quantum groups or quantum Kac-Moody algebras. You can apply similar story to the study of evolution of Heisenberg states and get Kvanov-Heisenberg categorification and generalizations. So, but I'm not showing the hard work of figuring out all the relations, but figuring out the relations is the fun and hard part. So now let's come to the PDG story. So we want to study two analogs of quantum groups at a pth root of unity. So we introduce on U a P differential. So locally it becomes a P differential graded algebra. So the definition is as follows. So define on U a derivation. So du is given by d acting on a dot becomes two dots. So dxi equals xi squared, as we have seen for the polynomial algebra case. And d of a crossing becomes this, this weird relation. D of crossing is identity minus 2 times the first dot times the Neo-Hack generator crossing. And d of caps and caps are given by these particular formulas. And it's not very hard as an exercise to show that indeed this is actually, it first off preserves all the relations of U. So in particular, it descends to the Lauda's calculus U, and is a P nilpotent operator over a field of characteristic P. So it's a P differential. So I think this is part of today's exercises to check some relations that D is compatible with the relations and it's P nilpotent. And so building on earlier theorem with Kovanov, Ben and I showed that the derived category of this this calculus with P differential categorifies the small quantum group UQSO2 at a pth root of unity. So And then our next goal is to show you how to outline how this is proved. So why the categorical relations of quantum groups are satisfied on the on this PDG calculus of U. The first goal, let's try to again adapt Lauda's decomposition of the projective modules in the triangulated category into something else. So this is because decompositions in triangulated categories are rarer. So what we get are filtrations instead. So in the realm of triangulated categories, direct sum decompositions are sometimes very rare. So instead, whenever you have a short exact sequence of PDG modules over some algebra U, or in this case, our 2 calculus, it gives rise to a distinguished triangle in the derived category, just as the usual homological algebra. When you have a short exact sequence of DG modules, you get a distinguished triangle. So to produce a distinguished triangle. So when it happens that these objects are compact, which we haven't defined yet, but you know that they give you a relation in the Grothendieck group. So the middle object becomes the sum of the object K and L sandwiching between M, okay? So more generally, whenever you have a filtered PDG module like that, so a short exact sequence is more like a one-step or two-step filtration. If you think about, if you filter M by sub-object and the quotient object is L. So more generally, if you have a filtration, you get a convolution diagram or a Postnikov tower in the algebraic topology sense, that the object can be presented as associated graded objects in the triangulated category. So, and then you get a relation in the Grothendieck group that the total object is just the sum of this its associated graded in the filtration. So adapting this abelian decomposition context earlier to the our explicit context. So we have that if you have a factorization of idempotents in the PDG algebra, so A like this, and if you can find a total ordering on I, so sorry, I should be emphasizing total ordering less or equal to on I, such that these two equations, VI dUI is 0 and UI composed with dVI is 0 mod lower order terms, or actually by conjugation you can do that for the first equation as well. It doesn't matter. So you just want to require that modulo lower order terms, that one of these equations is always 0, the other one of these equations is always strictly 0, the other equations is 0 modulo lower order terms. Then you automatically get a filtration on the PDG module A epsilon, whose subquotients are isomorphic to A VI UIs. Okay, so this is more general, so I'll give you a short proof. So in the situation above, then in the Grothendieck group, you get a relation like this. So of course, to prove the proposition, you define the filtration by adding more and more images of the idempotents UI VI. So in earlier context, we have seen UI VI is an idempotent. So when you add one more piece, so the associated graded is a UI VI. But under the assumption that that we have earlier in the proposition, then this Fi is actually declosed. So it's actually a PDG module over A inside the bigger module. This is because of this relation. And on the other hand, VI UI is also declosed because VI UI is the identity map, and D of the identity map is 0. And we get that there is a PDG isomorphism. So earlier in the abelian context, there's always an isomorphism AUI VI with AVI UI by multiplication by UI and VI, right? But the crux here is that UI and VI do not necessarily commute with G. They do not, they don't automatically upgrade to respect the PDG module structure. But under the assumption of the proposition that there is an ordering on this these idempotents, you do get this condition that the subquotients are isomorphic as PDG modules. So now you can use this proposition to check that under the differential, Lauda's factorization of idempotents actually does satisfy this condition. Okay, so it's a small computation now. So for instance, to check that under the differential, D of this guy is actually 0. So in particular, this map is a projection map from this this bigger module U of EF onto U times identity lambda. And the kernel of this map has another module of this map. There's another map onto the next piece, which I didn't draw, and et cetera, et cetera. So this presents U of EF as a convolution of the middle diagram. So in particular, you do get the relation we have seen for EF decomposition, even for this derived category of U and D. Okay, so I think I'm out of time. So next time I'll explain the other relation of nilpotency V, and together with towards categorification of tensor parallel modules over this quantum group. Okay, I'll stop here.
Okay. As before, we have exercises to work on where you get to play with these filtrations and sort of toy examples to try to see what it's like to upgrade a decomposition to a filtration. We have a question from Eugene in the comments, and people can ask questions before we move over to breakout rooms.
Is the filtration defining curves as 0? Yes, actually it is defining curves as 0. It's a great question. Yeah, it's defined over Z actually.
Yeah, it's in the exercise, but all these differentials are defined over Z, and all this stuff is really about Z. It's not really about characteristic.
Yeah, it's only when you specialize to characteristic P that you get D to the Pth power is 0.
So what is the representation theoretic interpretation of differential on Schur functions? I mean, derivatives are restrictions, but differentials are, I don't know.
It's a good question. I guess I'll refer you to my joint paper with Ben to see that these actions of these differential operators on Schur functions actually come from I don't know, there's actually a with algebra action. If you look at that paper by Lev and Michael in another context on link homology, actually you can deduce that that there are so-called with algebra actions on symmetric functions, or Heisenberg action. And this is just part of the data. You specialize to characteristic P.
So if it helps you, the formula is you take the differential of a Schur polynomial, you take the sum over all ways to add a box with multiple equal to the content of that box.
Yeah, the coefficient.
Oh, I see.
Yeah.
So it's some kind of version of induction, but not really.
Maybe.
Maybe.
Yeah.
I want to point out that there's kind of like an easier equivalent version of this, what it means to be a decomposition, which I've just sent to chat. To show that D of UI, VI, or whatever is 0, you basically just have to show this simpler condition that there's a filtration such that this is true.
Yeah.
A partial order such that this is true.
So if you have the higher differentials from the with algebra, like x to the k d over dx, do they preserve the filtration in any reasonable way?
Yeah, I think so. They do preserve the filtrations, I think. But we don't know what to do with them at the moment.
Well, one should be a little careful there because there's also the degree -2 one.
Yeah.
Which actually preserves the opposite filtration.
Ah, yes.
I can tell you more about this, Eugene, if you ask me. All right, I think we should go to some breakout rooms and work on some exercises.